Right, welcome everyone. Today, Patrick Wynne, the graduate student at CU Boulder, is going to talk about clonoids and nilpotent algebras.
Thank you, Peter. So, thank the organizers for inviting me to talk here today. Let me share my screen. Okay, so today I'd like to talk about some recent work on clonoids and some applications to some problems about nilpotent mouse of algebras. So this is joint work with my PhD advisor, Peter Meyer. So the first thing to talk about is function class composition. So if you were here last week, you've seen Erko give a similar talk. For non-empty sets, A, B, and C, if we have a collection of functions of arity m from A into B, and a function of arity n from B into C, then we can compose these functions to get a function of arity m from A into C as follows. So F composed with G1 through Gn, just inputs x and outputs f of G1 of x through Gn of x. So this is just our normal composition of multivariate functions. So if we have a collection of functions now from Bn into C and a collection of functions from An into B, we define the function class composition by just denoted just with juxtaposition Fk, and Fk is just all of the possible combinations, the compositions rather, of functions from F and functions from K, where the arities match up. So this is function class composition was defined maybe first in a paper of Cusero and Foldish, which I'll also reference later on. So, for example, with this notion of function class composition, we can define a clone quite easily. So a clone is a subset of functions from powers of A, finite powers of A, into itself, such that this subset of functions contains all of the projections and is closed with respect to all the possible compositions. So JA here denotes just the set of all projections on A. So if the composition of D and D is again contained in D, and the projections are in D, then we call D a clone on set A. Okay, so from an algebra, we can form the term clone, and so for basic operations, G1 through G2, etc., we can compose these functions to get new term functions. For example, we can get a k-ary function that's composed from basic operations G1 through Gn, which have arity k, and another operation f, which is a basic operation of the algebra, which has arity n. And this gives us then a function of arity k, which is formed from composition of our basic operations. So we call this the term clone of A, and just denote it by CLO of A. So, for example, if we have just a finite dimensional vector space over some field F, then with operations addition, negation, and constant zero, as well as a scalar multiplication for each element of our field, then the term clone is just the linear combinations of variables from A. So nothing new here. And similarly, if we have the integers as a ring, so we have addition, negation at a constant zero, as well as a multiplication and a constant 1, then the term clone of B is all of the polynomials, the classical polynomials in arbitrarily many variables, finitely many variables. And so maybe just to note here, really, I'm thinking about these elements of the term clone as functions. So on the right, I'm thinking of the induced function of the corresponding polynomial. Okay, so this is what a clone is. That's probably not why you're here. You're probably here to hear what a clonoid is. So I'll define a clonoid from a set from an algebra A into an algebra B to be a subset of functions from finite powers of A into B, such that this set C is closed first with respect to composition of term functions from A, and then in B closed with respect to composition with term functions from B. So first we can operate in A, then map from A to B, and then operate in B, and this new function that we obtain is still in our clonoid C. So for example, if we have the abelian group Z3 and as our A, and B is the two-element lattice, and C is a clonoid from A to B, well, if we have a binary function from A squared into B in our clonoid, then we can form a new function by first precomposing with some term operation of A, just this linear combination, and maybe here a constant 0, and here similarly a linear combination in both coordinates. Now these new functions are both inside of our clonoid C, and also we can operate with operations of B after we map into B. So if we then take the join of these two functions, we get a new function that still remains in our clonoid. So these clonoids are our primary object of study, at least for the first part of this talk. And then in the second part of the talk, we'll see some nice applications of clonoids, see how we can actually use them to solve some nice problems. And I'll just denote by angle brackets F to be the clonoid generated by some function F, is the smallest clonoid containing that function F. I'll also use these angle brackets later to denote clone generated by some function, but it should be clear from context which generation I mean. Okay, so in clone theory, the clones are determined by relational pairs. This is the famous Paul-Inv-Galois connection, and this is similar to what happens for clonoids. But for clonoids, we instead of considering relations, we have to consider pairs of relations. I think I misspoke. Clones are determined by relations. Clonoids are determined by pairs of relations. So for some relation of arity n on A and some other relation S of arity n on B, so the same arity of both of these relations, we call the polymorphisms of this relational pair Rs be all the functions from powers of A into B that preserve this relational pair. So it maps tuples from R into a tuple from S. So here my elements are just tuples, n tuples, where now I'm thinking about taking this function component-wise. So F of the first component, then F of the second component, etc. Now this new tuple that we get should be in our second relation S. So Cusero and Foldish, they showed that polymorphisms exactly describe clonoids in the following sense. So if we have algebras A and B with the size of A, the underlying set of the algebra A, finite, then a subset of functions from powers of A into B is a clonoid exactly when C is determined by some set of relational pairs. And these relations are actually subalgebras of powers of A. So we have, in general, for some relational pair, the polymorphisms might not be a clonoid from the algebra A into the algebra B, but if we require then that these relations are actually subalgebras, then we get a clonoid. And this condition that A is finite really can be relaxed to we don't need A to be finite, but this condition won't really matter for us since we'll mainly consider just finite algebras A. Okay, so for example, if we have A to be the integers modulo 9 with addition, so just the abelian group, and B to be the abelian group of 2 elements, then the polymorphisms of the relational pair 3 times Z9 and 0, so here 3Z9, of course, is a subalgebra of Z9 to the first power, 0 subalgebra of Z2 to the first power. This is a clonoid of functions from A to B, and it's exactly the functions that are mapped 3 times Z9 into 0. And similarly for the same A and B, we can think about equivalence modulo 3 as a subalgebra of A squared, and similarly equality as a subalgebra of A squared. And this is a clonoid from Z9 into Z3 that's constant on blocks modulo 3. So if we change our input modulo 3, then our output remains the same. Okay, and I already mentioned the intersection of clonoids, but now here maybe I'll make it explicit that the clonoids from an algebra A into an algebra B, they form a lattice, and the meet is given by intersection, and the join is given by the clonoid generated by the union. So the smallest clonoid containing both C and D. And maybe I'll just mention that if the algebra B has a constant operation, then since every clonoid has to preserve in particular this constant operation, then we get a smallest element of this lattice, which is just the functions that map to that constant. For example, for B equals to Z2 here, just like this example, the smallest operation is just all of the constant 0 functions of arbitrary arity. Okay, so clonoid is a subset of the set of functions from powers of A into B, and so a priori this could be size continuum, but at least for suitably nice algebras, we get that this clonoid is not determined by a whole bunch of relational pairs, but it is actually just determined by a single relational pair. So this theorem is due to Erhard Eichinger and Peter, and says that if we have a finite algebra A and a finite algebra B, where B has a Malsev term, then actually clonoids from A to B are finitely related. So really they prove something more general. We can replace Malsev term here with an edge term, but for this talk, Malsev term is exactly the case that we want to focus on. So if B has a Malsev term, then actually the clonoids from A to B are determined by finitely many relational pairs, and then from finitely many relational pairs, we can boil it down to just a single relational pair. Okay, of course, modules have a Malsev term given by x minus y plus z. Maybe for the non-experts in the field, a Malsev term is a term such that a ternary term such that if the first two elements, the first two inputs agree, it outputs the third input, and if the second two inputs agree, it outputs the first input. So if x and y are the same, then we get z. If y and z are the same, we get x. Okay, so this gives us an upper bound since the clonoids from A and into B are determined by a single relational pair. Of course, there's only countably many relational pairs. These relational pairs, each relation is just a subset of a power of A. So we get then that for modules A and B, finite modules, the lattice of clonoids from A to B is countable. Okay, so that gives us an upper bound on the number of clonoids, and now we'll see that in some cases we actually obtain this upper bound, that actually for certain pairs of algebras of modules A and B, we actually get countably infinitely many clonoids. So for A and B finite modules whose orders are not coprime, then the lattice of clonoids from A to B is actually countably infinite, and there exists non-finitely generated clonoids. So I'll sketch the proof for just the case where A and B are the integers modulo P, and I should mention that this proof for the integers mod P, this was originally proven by Sebastian Kreiniker, and he actually gave not just that there's some non-finitely generated clonoids, but actually that there's infinitely many non-finitely generated clonoids. So I'll just give one example of an infinite chain of clonoids here. So if P is a prime, and we have the integers mod P as our module A and our module B as well, then we can consider the function that just takes the product. So x1 through xn maps to just the product of x1 through xn, where here this is just our normal product in ZP. Okay, so then I claim that the clonoid generated by F1 is strictly contained in the clonoid generated by F1 and F2, and this is strictly contained in the clonoid generated by F1 through F3, etc. And so now this gives us then a strictly increasing chain of clonoids from A to B, or from A to A in this case, which then gives us the result. So the idea is that this function Fn takes x1 through xn and maps to the product x1 times x2 up to times xn. If any of our xi's is 0, then our output is just 0. So we call Fn like this a zero absorbing function. So we can show then that actually in the clonoid generated by F1 through Fn, if we look at the functions of higher arity, of arity say n+1, then there actually are no clonoid or are no functions that are zero absorbing except for the constant zero function. So, and the idea here is that essentially each of our components of some function, say of arity n+1 in the clonoid generated by F1 through Fn, some function of large arity in here looks like in each component looks like just a polynomial of degree n over ZP. And so then we can't have a zero absorbing polynomial like this unless our number of variables is small, less than or equal to n. Okay, so this gives us at least one chain of infinitely many clonoids from ZP into itself. Turns out, of course, there's a whole bunch more chains such as this due to Kreiniker. Okay, and in other cases, we don't obtain our upper bound. So there's in general for modules, there's most countable for finite modules, there's at most countably many clonoids, but in some cases the number turns out to just be finite. So Stefano Fioravanti showed that for a prime P, if we take the algebra A to be the integers modulo P, and B to be some other finite abelian group whose order is co-prime to P, then actually every clonoid from A to B is generated by its subset of unary functions. And since A and B are both finite in this case, there's only finitely many unary functions, and so then there's only finitely many clonoids from A to B. And the idea of the proof is if we start with some function of arity k from ZP into, I'll just sketch the proof for B equals to ZQ here, then we can interpolate this function on lines that pass through the origin. So specifically what I mean is that if we have some vector in ZP to the k, then we can look at the unary functions generated by this k-ary function f, and these unary functions now generate a function of arity k, which looks like f on the line generated by V, and it's 0 everywhere else. And then we can just do this for each line V. So if we choose for each V just generating a distinct line, then adding them all together, we get that our original function f is then generated by these FVs, just the sum of these FVs, because these lines almost don't intersect. Of course, they all intersect at the origin, but we can pretty easily reduce to the case where our original function from ZP to the K into ZQ is already 0 at the origin. So, and this idea will come up later in the generalization of this proof. So the important thing here is that we not only get that this function FV is generated by F, but it's really generated by the unary functions that are generated by F. So we start with F, a k-ary function. We look at the unary functions in the clonoid that it generates, and from those unary functions, then we can reconstruct the function f. Okay, so for A equals to ZP and B equals to ZQ for different primes P and Q, we get that there are just finitely many modules, or finitely many clonoids between them. And when the orders are not coprime, there are countably infinitely many clonoids between them. So the question is, if A and B are finite modules of coprime order, is the lattice of clonoids from A to B finite, or maybe it could still be countably infinite? Okay, and I posed it as a question because I don't have the full answer yet, but luckily at least we have a partial answer. So before I can state my partial answer, I'll just say that a module is distributive if it has a distributive submodule lattice, or equivalently, the congruence lattice is a distributive lattice. So this theorem is due to myself and Peter Meyer. For A, a finite distributive R module, and B, a finite S module, where A and B are of coprime order, then here n is the nilpotence degree of the Jacobson radical of R, then we get that every clonoid from A to B is actually generated by its subset of n-ary functions. And therefore the lattice of clonoids from A to B is a finite lattice. So we have this pesky word distributive here. Of course, if we could get rid of this word, that would be quite nice. But for now, this is the result that we have. And again, we have finite A and finite B. So each clonoid is generated by a subset of n-ary functions. There's only finitely many n-ary functions between finite sets. And so that's where we get the finiteness result for the lattice of clonoids from A to B. Okay, so for an example, or maybe real quick, just comparing this to Stefano's result, we have that the nilpotence degree n here gives us that the clonoids are generated by their n-ary functions. Just comparing it to the former result here for A equals to the integers mod p, the Jacobson radical of ZP is just zero, yeah, it's just zero. And so then this gives us that we get a unary generation for these functions. Okay, so I'll just sketch an example for A equals to the integers mod 2 and B the integers mod 3, just as abelian groups. If we take a function of arity 2 from A into B, then our theorem says that F is generated by its unary minors. Here by minor, I just mean the unary functions in the clonoid generated by F. So we look at the clonoid generated by F, all of the unary functions there, we'll call them unary minors of F. And for example, we have this function, f of x and x, just replacing each variable with the same variable x. This is a function, this is a unary minor of f. Now we have a function of just one variable, and it's generated by our binary function f. And similarly, f of 0 and x, f of x and 0, and f of 0 and 0 are all minors, unary minors of our function f. And so from these unary minors, we can reconstruct then our original function f. F of x1 and x2 is just given by f of 0, 0 plus all this mess here. And for this simple case of A equals to Z2, it's somehow straightforward to just verify that this equation holds. And I wrote here 2 inverse. So this is in the integers mod 3. Of course, the inverse of 2 is again 2. I just wanted to stress the importance that A and B are actually of coprime order. So 2 is invertible inside of Z3. And one thing to note about this equation here is that this equation it holds independently of our choice of F. So nothing about this generation of F from its unary minors depends on our actual function F. So we have this nice sort of, we can think about it as a generalized linearity condition of all functions from A into B satisfy this equation. All binary functions and all functions of higher arity will have an analogous equation like this. Okay, so here's a specific version of the theorem that we had. So where A is the integers modulo p to the power n for prime p, and B a finite abelian group whose order is coprime to B, then our theorem says that every clonoid from A into B is generated by its subset of n area functions. So I'll just sketch the proof for this simplified case where A is just this abelian group. So just like for the proof from Fioravanti, we want to start with the function f of arity k. We'll look at the n area functions in the clonoid generated by f, and then we'll reconstruct f from these n area functions. So in the first proof for a equals to zp, we reduced to the case where the functions take 0 and map to 0. So here we'll similarly reduce to the case where f is 0 on p times a, which is the unique maximal subgroup of zp to the n. So to reduce to this case, essentially we just go by induction on the submodules, or in this case subgroups of a. So we reduce to this case where the function disappears on its maximal submodule, and we look at the n area functions generated by f, and then from those n area functions we can generate another k area function which looks just like f on some subset here, and it looks like 0 everywhere else, and this subset is exactly a in the first component, and then all the other components are coming from p times a. So if this is the picture for k equals to 3, well then our function looks like f on this red cube here, a red rectangular prism, and the function is 0 outside of here. Okay, so sorry for the people in the room that can't read this line right now, but for n, a submodule of a to the k, or a subgroup of a to the power k, such that, let me just escape just for your sake, that n is above pa to the k, and n modulo pa to the k is isomorphic to a modulo pa. So for example, one n like this is this red region that we had here, a times pa to the power k minus 1. So now for all n's that essentially look like this a times pa to the k minus 1, we can generate a function that looks like f on this submodule n. So from the n area minors again of our function, of our k area function f, we generate a new k area function which is equal to f on n and is 0 outside of n. So again, we start with a k area function, reduce to n area functions, and then reconstruct our k area function from those n area functions. And now we can cover all of a to the k by subgroups of this form. And now, just like in the original case for zp, they intersect. So, but now we reduced already to the case where they're going to intersect on just p times a to the power k, and so they intersect where the function is already 0. So then f is just the sum of all of these fn's. So then we can reconstruct f from its n area minors, and so that shows then that every clonoid, in fact, from A into B is generated by its subset of n area minors. And just like before, we get this nice generalized linearity condition. So first, maybe I'll just mention, we define the rank of a matrix over an arbitrary ring as the least L, such that the columns of L generate a submodule, which is L generated. So this is, of course, just our normal notion of rank if R is a field. So now, just like for the ZP case, I had that example of a binary function generated by its unary minors that didn't depend on the function f itself. And here we have something similar. So for the exact same setup as before, A is finite and distributive, and B is a finite S module, and the two modules are co-prime. Then we have a function S here that takes in our matrices of rank n, k by k matrices of rank at most n, and outputs elements of S of the ring over which B is a module, and we get then that F for any F is equal to the sum of S of R times F of R times X. So we have this nice linearity condition that holds again for any function F from one finite module, which happens to be distributive, into another finite module of coprime order. So this doesn't depend on F here. This choice of our function S doesn't depend on F. So really, if you try to distill this from our proof, you'll just get that for each F, there is such an S, but actually we get something stronger that this S works for every function F. And so we'll state this phenomenon by saying that the set of k-ary functions from A into B is uniformly generated by its n-ary minors. So not only can we get F from its n-ary minors, but we can do it in the exact same way for any F. For any, it doesn't actually depend on our choice of function F. And we can use this uniform generation to actually generalize not from modules to abelian Mal'cev algebras. So I'll just talk briefly for a second about what is an abelian Mal'cev algebra. So an algebra is abelian if the commutator of the largest congruence on A with itself gives us the trivial congruence. So here, this is just our normal commutator. If you haven't seen the commutator before, just think about it as the group commutator. So we just have G commutator G is equal to the trivial subgroup. So an algebra A is in a congruence modular variety is abelian exactly when it's polynomial equivalent to a module over a ring. So by polynomially equivalent here, I mean that if we expand our algebra A with all of its constants, then this new algebra that we obtain is just a module over a ring. And here's the ring here. So if we fix elements Z and X as our neutral elements, then we get a ring that we can form from our binary terms. So I don't really want to go into too much detail other than just to note what this ring actually is. And then our module is given by, we have addition given by, again, fixing a constant 0. We get addition and negation with respect to our Mal'cev operation, and scalar multiplication similarly. So if we could just expand by constants, then a abelian Mal'cev algebra just is essentially a module over a ring. And so now we'll generalize our result to, instead of A and B being modules, to A and B being abelian Mal'cev algebras. So if A is polynomially equivalent to a distributive RA module, and B is polynomially equivalent to a finite RB module, again, so that A and B are co-prime, and N is the nilpotence degree of the Jacobson radical. So now the exact same setup as before, except now I replaced A is a module to A is polynomially equivalent to a module, and similarly for B. Then we get that every clonoid from A to B is generated by its subset of n+1 ary functions. So we pay a little price here. We have an n+1 instead of an n. And the lattice of clonoids from A to B is still finite. And so this change from n to n+1 is essentially because we have to sort of make up for this lack of a constant with an extra variable or an extra projection. Okay, and similarly, we get that the functions from abelian Mal'cev algebra A into abelian Mal'cev algebra B are uniformly generated. So just like before, we have this nice equation that for any function f, we have, of course, we have a function S that maps our matrices of rank at most n into our ring RB. Then we get for any f, we have this generalized linearity condition between functions from A into B. So maybe a lot to take in on that slide there, but essentially we have something going on just like for the module case with now an extra variable floating around. Okay, so for the normal notion of the center of an algebra, we can, so the center of an algebra is the largest congruence alpha, such that alpha commutator 1 is the trivial congruence. And Friese and Mackenzie showed that in a congruence modular variety, for an algebra A, there exists an algebra L in this congruence modular variety, such that A is isomorphic to a central extension of L by U, or I'll read this as L reth U, where here U is just A modulo its center. And this L reth U is an algebra whose universe is just the product of L times U, and all of the basic operations look like they take in tuples L1, U1 up to LK, UK, and they spit out in the second component, let's say, first just F applied to U1 UK, F interpreted in U, and in the first component we have F interpreted in L applied to the L's, plus this distortion F hat applied to the U1 through UK. So somehow we have the upper part acting on the lower part. So this is sort of analogous to central extensions in group theory, but now here I'm just assuming that A is coming from a congruence modular variety. And this function F hat is a function then that takes in U1 through UK and spits out an element of L. So this is what I'll call a central extension of L by U. And so just like all of the basic operations have this form, all of the terms also have this form. They look like TL of the L's plus some distortion T hat of U, and then in the second component, TU of the U's. So sort of a boring example, if we take the direct product of L times U, this is central extension where all of these T hats are just 0. So this is just TL in the first component, TU in the second component. So maybe the most boring example. And now we can compare arbitrary central extensions to this direct product. So if we have an extension of L by U in a congruence modular variety, with the assumption that we have this one element subalgebra of L, then we have this psi is from clone of L reth product U into the clone of L direct product U, given that takes some function F and maps it to the interpretation of F in L times U. This is a surjective clone homomorphism. And this function is injective exactly when this central extension is already just the direct product. Okay, so what happens when this clone homomorphism is not injective? Well, we'll define the difference clonoid, which I'll denote by D of L reth U, to be all the functions that map from U, from powers of U into L, that look like just the first projection plus some distortion U1 through UK. So the difference clonoid is all of these functions that we can tack on to this first projection to get a new function that still remains in the clone of L reth U. So, of course, D L reth U is a clonoid. The proof is, well, we called it the difference clonoid, so hopefully it's a clonoid, or else that's a bad name. And so for any function F in our clone of L reth U, and any function E from U to the K into L that's in our difference clonoid, we can add these functions together and we get a new function that's still inside of our clone of L reth U. And the pair F and F plus E is in the kernel of this clone homomorphism for every E in the difference clonoid. So here I'm abusing notation a little bit. F plus E here, I'm thinking about F plus E acting on tuples LU by FL of L plus F hat of U plus E of U, and then FU of U in the upper component. So I'm just adding this E just to the lower component here. Okay, so in a congruence modular variety, we have a difference term D, And for any central extension of L by U, we can characterize when we can give a generating set for the clone of L reth U. So if G is a subset of L reth U such that psi of G generates the clone of L times U, which exists because this clone homomorphism was surjective. And if E is a generating set for the difference clonoid, then the clone of the central extension of L by U is generated by the generators G plus our difference term D, as well as essentially our difference clonoid. Here I'm just adding them to the first projection so that they're actually elements of this term clone. So for abelian algebras in a Malsev variety, or I should say in a congruence modular variety, they're term equivalent to an algebra with ternary basic operations, or put a different way, the clone of an abelian algebra is generated by its subset of ternary functions. So if U happen to also be abelian, then the clone of L times U is generated by ternary functions, because now L and U are abelian, so their direct product is still abelian. And so that's the case that we'll take a look at. So if A in a congruence modular variety is 2 nilpotent, that means that the iterated commutator is equal to 0, where we iterate exactly twice. So this is what a 2 nilpotent algebra is. And now just translating the theorem from Friese and Mackenzie into this setting, we get that an algebra in a congruence modular variety is 2 nilpotent exactly when A is an central extension of L by U, and L and U are both abelian. Okay, so now we can understand this situation better, because now we have a handle of the difference clonoids for the abelian L and U. So if L reth U is a central extension of L by U, this is a 2 nilpotent algebra in a congruence modular variety, then if we have that the difference clonoid is finally generated, then the term clone of L reth U is also finally generated. And in the specific setting where we know about the clonoids, now we can say exactly that if L and U are co-prime and U is polynomially equivalent to a distributive module with Jacobson radical having nilpotence degree n, so the exact setup that we had before, then the clone of L reth U is generated by its functions of arity at most 3, the max of 3 and n plus 1. So the second, this is repeating the same theorem here. The second bullet point is exactly the situation where we understand already the clonoids from U into L. So L and U L reth U is 2 nilpotent, so L and U are both abelian. So the clone of L times U is generated by its ternary functions. And if this difference clonoid is also finally generated, then we get that the term clone of L, the central extension of L by U, is finally generated just from the previous theorem. And now in the case where we understand the clonoids from U into L, then we have that every clonoid from U into L is generated by its subset of n plus 1 area functions, and then putting that together, we get the result that the term clone is generated by its subset of functions of arity max of 3 and n plus 1. Okay, so now we get a nice corollary to this for a square-free M. The number of 2 nilpotent algebras, Malsev algebras of order M, is finite, where we consider the number up to term equivalence. So 2 algebras are the same if they have the same term clone. So the idea is that if we have a central extension of L by U, which is 2 nilpotent, then L and U are both co-prime, since M is square-free. So L and U are both abelian and co-prime. And so the congruence lattice of U is a distributive lattice. And so then also the congruence lattice of if we expand U by constants, then this congruence lattice is still distributive. So that says that U is polynomial equivalent to a distributive module. So this distributivity gets retained. And the clone of the L wreath U is generated by its functions of arity max of 3 and n plus 1. And of course, there's only finitely many such functions for finite L and U. And so then we get this result. And just comparing that to the situation where M is non-square free, if M is non-square free, then actually there's infinitely many 2 nilpotent Malsev algebras of order M. And this essentially is was already known before, and this was proven by Pavel Idziak, I believe, as well as Bulatov. And so we can also prove this using this same perspective of clonoids. Okay, so that's I guess that's the main results then for this talk, and I'll just leave with some future work and some questions. So right now we want to understand for a 2 nilpotent Malsev algebra of square free order. We know how many there are. Sure, that's all well and good. We'd like to know, are they all finitely based, and do they have tractable subpower membership problem? And this is the question that I had before: is every clonoid between finite Malsev algebras of coprime order finitely generated? Can we get rid of this assumption that our algebra, the source of our clonoid is a distributive module? Can we get rid of that distributivity assumption? And what about for instead of 2 nilpotent algebras, what if we want to consider k nilpotent algebras for k greater than 2? Is there still finitely many k nilpotent algebras on a set of square free order? And for this, now our U would not be an abelian algebra like we had in this nice case, but U would instead be a nilpotent algebra of nilpotence degree k minus 1. And so we'd likely, in order to answer this question, have to understand not clonoids between modules, but clonoids from a nilpotent Malsev algebra into a module. So yeah, so that's all for now. Here's the link to a paper of Peter and mine that contains essentially the first half of this talk's results. And yeah, so.